Good evening, class. We are looking at Chapter 5, Trigonometric Functions. The first section is about angles and their measures. We are going to cover angles and their measures, trigonometric functions, properties of trigonometric functions, and the objectives for this section are convert between decimal and degrees, minutes, seconds, measure for angles, find the length of an arc of a circle, convert from degrees to radians and from radians to degrees, find the area of a sector of a circle, find the linear speed of an object traveling in circular motion. Reminding you of the exponential functions are in the form of a to the power of x, where a is positive and can't be 1. When it's 1, it's not an exponential functions. Some exponential rules you are familiar with. Horizontal asymptotes. There is a horizontal asymptote. There is no vertical asymptote. The y-intercept takes place at 0, 1. Domain is all real numbers, ranges 0 to infinity. In this case, it's increasing. In this case, when a is positive 1, in this case, it's decreasing, and the end behavior. In this case, when x goes to infinity, y goes to infinity, the first quadrant. In this case, limit of f of x as x approaches minus infinity is 0. In this case, it's the other way around. The limit of f of x as x approaches minus infinity is infinity. The purpose of that is the following. Knowing the graph will give you all this information. You have to be comfortable. Logarithmic properties, we said, when the base, when we choose b to be positive and can't be equal to 1, this indicates the base for one is the base for the other, and this arrow indicates b to the power of y equals x. That will help with the properties we are going to show you, reminding everyone of those properties. Log 1 with any base is 0. Log b base b is 0, meaning if the base and the argument are the same, the answer is 1. And log base b of b to the power of x is x, b to the power of log x base b is x. These two refer to the fact that two functions, logarithmic and exponential functions, are inverse of each other's. Product rule, log x y is log x plus log y, all of them base b. Quotient rule, log of x over y base b is log x base b minus log y base b. And the power rule, log base b of x to the power of n equals n log base b of x. And if you go to common log, y equals log x, please do not write base is 10. We are explaining the meaning of that. In that case, we can see the transition. And also for natural log y equals ln x, we should be able to see the transition from general case to common log to natural log. Natural logs and exponential functions with the base e or inverse functions, so symmetric with respect to y equals x. Change of base formula, log x base b is log x over log b, same base, any base, for example a, but we choose either common log or natural log. And of course, I've mentioned that here this is 1 0, so ln x equals 0 at 1. And it's negative if it's between 0 and 1, and if it's positive, then it's x is larger than 1, it's positive. Exponential and logarithmic equations and interest. Remember, if exponential functions are equal, they have the same base, they must have the same exponent. If they have the same exponent, they must have the same base. Same thing for logarithmic functions. If they have the same base, must have the same argument. If they have the same argument, they must have the same base. Needless to say, x and y and a and b, they're all positive. Simple interest rate I equals PRT. Compound interest rate A equals P times 1 plus R over N to the power of NT. P is the principal, R is the rate, T is the time in years, N number of times it gets compounded per year. And if it's compounding continuously, A equals P e to the power of RT or P sub 0 e to the power of KT. R or K is the growth rate. It is also known as a future value. So if you want to calculate P sub 0, you can divide by e to the power of KT. Doubling time, the time it takes for a population or an investment to double in size, and we've shown that T equals ln2 over K. The effective rate of interest is the equivalent annual simple rate of interest that would yield the same amount as compounding after 1 year. In the case of the compounding that was mentioned here, R is 1 plus R over N to the power of N minus 1. In the case of a continuous compounding, R equals e to the power of R minus 1. This is the synopsis of what we covered previously. And now the new stuff. Angles and their measurements. We start with some definitions. Vertex line rate. Here's a line, everybody. Goes indefinitely in both sides. Here's the vertex, where two line segments, okay, two half lines come together, called ray. Each one is called ray. We're going to look at the initial side and terminal side. Here's the angle. Here's the vertex when the two sides come together. Initial side, terminal side, and we are looking at rotation counterclockwise as positive angle. We have the initial side, we have the terminal side. Clockwise, it's negative angle. Vertex line ray, initial side, terminal side. Positive angle, negative angle. Standard position. Here's the initial side, here's the terminal side, and we've covered more than one revolution. It is still counterclockwise and it's positive. Now, what is standard position? The initial side is along the x-axis. So, theta is in standard position, theta is positive. So, the initial side is along the x-axis, is called standard position. Terminal side. This happened to end up in the second quadrant. Quadrant 1, 2, 3, 4. And in this case, again, we have the initial side along the x-axis. However, clockwise, the terminal side is in the third quadrant. Theta is in standard position, but theta is negative because of the rotation. So these are some definitions, basic definitions. You may remember from trigonometry. Coterminal angles are angles that share the same terminal side when drawn in standard position with their initial side along the positive x-axis, they may differ by an integer multiple of 360 degrees or 2 pi radians. For example, if you look at this angle, okay, if you go a complete revolution, come back to the same, or this angle, you go a complete revolution and come back to the same spot. As you can see, this one, for example, in essence, it could represent two coterminal angles. One of them starts from here and ends here, right here, or one of them may go a complete revolution plus this much. And that's the idea of coterminal angles. So therefore, multiples of 360 degrees or 2 pi radians. Quadrants and quadrantal angles. Of course, everybody remembers, just as we dealt with algebra. Here's the first quadrant, where theta is between 0 and 90 degrees. So here's a 0, here's is 90 or power 2, here's 180 or pi, here's 270 or 3 power 2. Quadrant 1, theta is between 0 and 90, quadrant 2 between 90 and 180, quadrant 3 between 180 and 270, and quadrant 4 between 270 and 360. So those are the 4 quadrants. Quadrantal angles. Quadrantal angles have a terminal side that lies on the x-axis at 0 degrees, or 180 degrees, or the y-axis at 90 degrees, or 270 degrees. Meaning, it just lies along the x-axis on the right or left, that means positive or negative, or on the y-axis up or down. It's that simple, everybody. Quadrantal angles. We continue with the definitions. Quadrants, right angle, straight angle. So here's in quadrant 2. Theta lies in quadrant 2. Here's theta lies in quadrant 4. We're talking about the terminal side, because when it's in standard position, we know that the initial side is along the positive x-axis. In this case, theta is a quadrantal angle because the terminal side is along one of those axes, x or y. In this case, it's along the negative side of the y-axis. Complete revolution, the terminal and initial side are both on positive side of the x-axis. That means 360 degrees, or one revolution positively, that means counterclockwise. The initial side along the positive side, of course, of the x-axis, the terminal side along the positive side of the y-axis gives rise to 90 degrees angle. This is called a right angle, 1/4 of a revolution, counterclockwise, 90 degrees. Initial side, of course, along the positive x-axis, terminal side along the negative x-axis. This angle is called straight angle, half of revolution, counterclockwise, 180 degrees. So quadrants, right angles, straight angle. Right angle, straight angle. All right, we want to draw angles, and remember the initial side is along the positive x-axis, so 45 degrees along the x-axis, and you go counterclockwise 45 degrees. That would be the terminal side. Very straightforward. So we start from this one and we go that way. Now for 90 degrees, you go to the counterclockwise, but for negative 90, we go down. The terminal side would be the negative side of the y-axis, so negative 90 degrees, looking like that. 225 degrees. So from here, you go 225 degrees. And this is 180, so go a little bit more, about 45 degrees more, results in 225 degrees. Counterclockwise for a positive side. 405. That means this is larger than 360 degrees. So you go a complete revolution. And then 45 degrees. In other words, this much. And these two would be examples of coterminal angles. These two. This one and this one are coterminal angles. Just as an example. So pretty straightforward. We are going to move on. All right. Convert between decimal and degree, minute, second, measures for angle. So one counterclockwise revolution is 360 degrees. 1 degree is 60 minutes. 1 minute is 60 seconds. Convert 40 degrees, 12 minutes, 5 seconds, to a decimal in degrees. Round the answer to 4 decimals. So to do so, if 1 degree is 60 minutes, then 1 minute is 1 over 60 degrees. And 1 second would be 1/60 times 1/60 degrees. I hope everybody understands what's happening here. So 40 plus 12 times 1/60, because each minute is 1/60 degrees, plus 5 times 1/60 times 1/60, which is 1/3600. 1 second is 1/3600 degrees. So it's pretty straightforward. I hope everybody is fine with that. You put it into a calculator. This is 0.2, this is 0.0014. You add them up, you get 40.014 degrees. And of course, you carry the number of decimals that they ask you. Convert 78.562 degrees to the DMS, degrees, minutes, seconds form, and round the answer to the nearest second. So we have 78 degrees plus this much. Now, this one is in degrees. If you want to go to minutes, we are going to multiply this by 60. So we multiply by 60, this is what we get. We have the 78, and this one is in minutes. 33.72 minutes. In other words, 78 degrees plus 33 minutes plus 0.72 minutes. This one, each minute is 60 seconds. Let's multiply it by 60 seconds. This is fine. This is fine. This one, we multiply by 60 seconds. And that, this doesn't change, this doesn't change. This becomes 43.2 seconds. And since we are going to round to the nearest second, 43 next to it is 2, it doesn't change. Remember, if this is 5 or higher, this changes. So we are going to write 78 degrees, 33 minutes, and 43 seconds. So that's pretty straightforward. Radian definition. The measure of a central angle subtending an arc equal in length to the radius, and it's almost 57.3 degrees. 180 divided by pi, precisely 57.3 almost, which means If you look at these two cases, in this case, R, and this arc must be equal to R. This measures 1 radian, regardless of the fact that it's a small circle with radius 1 or larger one with radius 3 or any other size, as long as the radius is equal to the arc that this angle covers. Find the length of an arc of a circle. And we remember the circumference, a complete revolution is 2 pi r. So we write the arc length is the length of the arc of a portion of a circle, part of the total circumference of a circle. Given the central angle theta, S equals R theta. Think about it. So the ratio of theta to theta 1 is S to S1. So more importantly, think about this. The circumference is 2 pi r. Again, a complete revolution. So 2 pi represents a complete revolution, represents the arc. So a specific arc which has a radian measure of theta, in fact, 2 pi is theta. For a complete revolution, this theta is 2 pi. Therefore, S equals R theta. Again, going with S equals R theta, if theta is 2 pi radians, that's what we get, 2 pi r. Find the length of the arc of a circle of radius 4 meters subtended by a central angle of 0.5 radians. So S equals R theta. S equals R, which is 4, times theta, which is 0.5, resulting in 2, and the units are the units of the radians, which were in meters. By the way, any applications, if units are given, you want to answer them with proper units. Theta must be in radians when you calculate the arc length. Convert degrees to radians and radians to degrees. Definition: 1 revolution is 2 pi radians. 180 degrees, therefore, is pi radians. 1 degree is pi over 180 radians, and 1 radian is 180 over pi degrees. So a complete revolution, 360 degrees, or 2 pi radians. So one revolution, right? So that's important to know. So we go with the easy formula D instead of having to memorize it. D over 180 is R over pi because pi radians is 1 over 80. So if the degrees are given, you put it here, you find the missing radian. If the radians is given, you put it here, you find the missing degrees, or this is the conversion, pi over 180 or 180 over pi, depending upon what you need. So some of the common angles or arcs that you should be familiar with. You can find them here. I hope you remember those. Obviously, 30 degrees is pi over 6, 45 degrees pi over 4, 60 pi over 3, 90 pi over 2, 122 pi over 3, 135 3 pi over 4, 155 pi over 6, 180 is pi, and the rest of them. Okay. Those are some common arcs. Convert from degrees to radians. So you have two choices. You can say, I'm going to go from degrees to radians, so I'm going to multiply by pi 1 over 180. Or say, for example, here, put the 30 here, and cross product, find the missing r. Of course, we've already established this is pi over 6. I hope you're okay with that. But here's the justification with details, if you will. So 30 degrees is pi over 6. So if you multiply it by pi over 180, 30 cancels out the 180. This goes away, this becomes 6. Same thing here, times pi radians over 180. Both of them can be divided by 60. This becomes 2, this becomes 3, 2/3 pi. Minus 60 times pi over 180, 60 cancels out this one, and this becomes 3, but remember the negative sign. Now, 104, I wanted to make a point here, and that is, now you have a number that you, in essence, going to put it in a calculator times pi. And pi, please understand, is not 3.14. It's approximated by that. Put it into a calculator, and however many decimals they ask you, normally they, in a case like that, they may ask you. If they don't, these are the exact values. 1.815 rate. Now, for B, convert from radians to degrees. So this time we're going to multiply by 180 over pi. For example, here clearly the pi's cancel each other. 180 over 2 is 90. Don't forget the negative sign, negative 90 degrees. Again, this is one of those common arcs. We should know that 5 pi over 6. Okay, so, or as I mentioned, d over 180 is minus pi over 2 over pi, as I was mentioning here. Either way, you should have no problem with that. 5 pi over 6 times 180, the pi's cancel out. 180 divided by 6, 30 times 5. Let me just quickly show. This cancels this one. This goes away, and this changes to 30, so 150 degrees. Times 180 divided by pi requires using a calculator with a bunch of decimals, and we end up with 286.48 degrees. Normally they use a couple of decimals, but just follow the instruction. All right, here's the application. Example 5. The latitude of a location L is the angle formed by a ray drawn from the center of the Earth to the equator, and a ray drawn from the center of the Earth to the location of interest N. So you have this, in essence, you can think of it as a horizontal line from the center of the Earth, from the center of spherical shape, from the center of the sphere, and then from there to the location that we are interested in. Glasgow, Montana is due north of Albuquerque, New Mexico. Find the distance between Glasgow approximately 48.15 degrees or 48 degrees 9 minutes north latitude, and Albuquerque approximately 35.083 degrees or 35 degrees 5 minutes north latitude. Assume the Earth radius is 3,960 miles. So when we look at this question, it's important to understand what's given and what's missing. Well, we are in essence looking for the distance S equals R theta. R is 3960. And theta, we need to find the distance between the two angles here. So let's see what's given. So these are the locations that they were discussed. Okay. So here's the center of the sphere, the Earth. Here's the location Glasgow. Here's the location Albuquerque. So we are interested in this distance, everybody. So let's make it larger so it becomes clear. So here's the equator, Albuquerque, Glasgow. We want this distance, everybody. So the radius is 3,960 miles. Theta 1 is 48.15. And theta is 35.083 degrees. If we want this distance, which is going to use S equals R theta, we need to find this theta. This angle. And this angle, the angle between the two cities, okay, between the two cities is the difference between the two angles. So the central angle between the two cities is the difference of the two numbers, everybody. And we get 13.067 degrees. Now, it has to be in radians. You have to multiply it by pi over 180 to change it in radians. It's a must. So again, I can't emphasize this enough. S equals R theta. Theta must be in radians. So now you multiply the theta that you found in radians by the radius of the Earth. The distance is about 903 miles. Pretty straightforward, everybody. Find the area of a sector of a circle formed by a central angle theta. A equals 1/2 R squared theta. Let's discuss that. Theta over theta 1 equals area over A1. We know the area of a circle is pi R squared, which means in order to really have an understanding that, let's call this 1/2 times 2 pi. And remember, this is a complete revolution, right? A complete revolution is 2 pi. So if you want area of a sector, you want 1/2 times theta times r squared. So 1/2 r squared theta. Believe it or not, that's the proof. Area is 1/2 r squared theta. Therefore, for this example, we want to find the area of a sector of a circle of radius 5 feet formed by an angle of 60 degrees. Area is 1/2 r squared theta. And we know 60 degrees is pi over 3. You must make that change because it has to be in radians. So 25 over 6 times pi, and that's, this class is an exact answer. And it's an approximation. As far as the units, units of the radius squared. Find the area of a sector of a circle of radius 2 feet form an angle of 30 degrees and 30 degrees. Pi over 6. Pi over 6. So half of r squared times pi over 6. So this is 4 divided by 2 is 2. Cancels out the 6. 2 goes away. We get pi over 3 precisely, or about 105, 1.05 square feet. Find the linear speed of an object traveling in a circular motion. Suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on this circle, then the linear speed v of the object is defined as distance over time. Linear speed is total distance covered over total time. The distance is arc length s, and the time is just t. So that's the definition of a linear speed. The angular speed has a similar definition. The angular speed omega, this is not w, omega, the Greek lowercase letter omega, of this object is the angle theta measured in radians swept out divided by the elapsed time t that is. So over here, s divided by 2 gives us v. Theta, the angle divided by t, it gives us the angular velocity. Now, here's the interesting part. V is s over t. We are going to replace the s with r theta. And we're going to separate the r from theta over t. If theta over t is omega, v becomes r omega. That's the relationship between the two velocities, okay? So one is linear speed, one is angular speed. Distinguish between the two. Here's a simple example for that. We want to find the linear speed. A child is spinning a rock at the end of a 3-foot rope at a rate of 160 revolutions per minute, short RPM. Find the linear speed of the rock when it is released in miles per hour. And I'm reminding you that 1 mile is 5,280 feet. And I'm writing the formulas. Omega is theta over t, or 2 pi times RPM, v is s over t, or r omega. Please understand that revolution, a complete revolution is 2 pi radians. So for example, 2 revolutions is 4 pi radians. 10 revolutions is 10 times 2 pi. So that's why we have 2 pi times RPM. So you're looking at an application, what is given? R is 3 feet. Omega is 160 RPM, revolutions per minute, RPM. So the very first thing we do, we are going to write this in radians per minute, which means we have to multiply it by 2 pi. So again, RPM, a complete revolution is what? 2 pi radians. So you have to multiply by 2 pi. I want everybody to understand why we are multiplying this by 2 pi. So this is the omega with revolution per minute. When we multiply it by 2 pi, becomes radian per minute. Okay, radians per minute. And 2 pi times RPM, 2 pi times 160, which makes it 320 pi radians per minute. So we made this conversion first. The next one, V equals R omega. And we know R, we know omega. So 3 times 320 makes it 960 pi. 960 pi is at 3016, and the units are feet per minute. Why feet per minute? Because the radius is in feet, 3 feet. Okay, pay attention to the units. But we want them in mph, we want it in miles per hour. So let's make the conversion. So we have the V almost, this is not precise, 3016 feet per minute. And we want to change this to miles per hour. Remember, 1 mile is 5,280 feet. So I can put this one at top of this as a fraction. It's called the unit conversion. Or I can put this one at top of that. Let me actually write both so you see what I mean. This 1 mile over 5,280 feet is called unit conversion. So is this one, 5,280 feet over 1 mile. They are the same, unit conversion. Now the question is, which one are you going to use and why? Remember, you want miles to be at top here. Okay? So you put the miles at top. 1 mile over 5,280. Okay? Hours, minute, 1 hour is 60 minutes. So you can say 1 hour over 60 minutes, or you can say 60 minutes over 1 hour. Since you want the hour to be at the bottom, you are going to put the minutes at top, hours at the bottom. Again, this is a unit conversion. Its reciprocal is a unit conversion. I want to show you, again, I explained why the mile is at top, because the result must be miles at top. And for the hours, I can write 1 hour over 60 minutes or 60 minutes over 1 hour. And I'm writing 60 minutes over 1 hour. Here's the reason, because we want to make sure we end up with this. So this cancels out this one. This cancels out this one. And I just want you to look at the units. The units left are mile in the numerator, hour in the denominator, and that's exactly what we have. As far as the numbers, you multiply this one by 60 and you divide it by 5280 and you get 34.3. So I wanted to make sure everybody's comfortable with this unit conversion. We're going to continue with this, finding the linear speed. An object is traveling around a circle with a radius of 8 inches. So R must be 8. If in 40 seconds, a central angle, so 40 seconds, the time is 40 seconds, of 1/3 radian is swept out, what are the linear and angular speed of the object? So first and foremost, you have to write what's given. So what's given is the radius is 8 inches. The time of interest, 40 seconds. Over the time of 40 seconds, we cover the angle theta equals 1/3 radians, okay? And we want to find the linear and angular speed. So R is 8 inches, T is 40 seconds, theta is 1/3 radians, omega is the angular velocity, V is the linear velocity, or angular speed, linear speed. So we know that omega is theta over T. So theta over T. 1/3 over 40 is 1 over 100 over 100, because it's 3 times 40. 1 over 120, or 0.008 radians per second, everybody. Radians per second. The units are important. I hope everybody is okay with that. V equals R omega. Well, we know R is 8. Omega, we want to go with the precise, not that one, because we have it available. And 8 and 120 are divisible both by 8. And this goes away, this becomes 15. Precisely 1 over 15, or roughly 0.07 inches per second. Y inches because R is in inches. The units follow. The minute hand of a clock is 6 inches long. The hour hand, the minute hand, the second hand. How far does its tip move in 15 minutes? Again, we have to write what's given. If the minute hand is 6 inches long, that means what? Right? Of course, it moves clockwise. R is 6. And in part A, we talk about 15 minutes. We need to find theta and therefore S. So R is 6 inches. In part A, 15 minutes will correspond to some angle we're going to find in a moment. And then S. Because how far does its tip move? That means, how much does it cover as far as arc length? S equals R theta. That's the bottom line. S equals R theta. We are interested in that. So 15 minutes, if the whole revolution is 60 minutes, so we are talking about 15 over 60 is the number of revolutions, or 1/4 times 2 pi, or pi over 2 radians. So 1/4 of a revolution. This revolution means 2 pi. Okay, everybody? And therefore, we have pi over 2 radians. So S equals R theta. We are going to multiply R, which is 6, by theta, which is pi over 2, and we get 3 pi precisely, about 9.42. And Y is it in inches? Units of the radius. Units of the radius, everybody. So we just follow the units properly. What about the same thing in 25 minutes? How about 25 minutes? And again, we are going with a couple of decimals. In this case, all you have to follow is find theta. Instead of 15 over 60, we're going to go with 25 over 60. Results in 5 over 12 times 2 pi is equal to 5 pi over 6. S equals R theta. Replace the theta this time with 5 pi over 6, everyone. And we get 5 pi precisely, roughly 15.71 inches. And again, the units, everybody, just follow the units of the radius. Inches. Example 10, a 40-inch pendulum swings 20 degrees each second. How far does its tip move each second? And they want it with 2 decimals. Here's the concept of a pendulum, right? And here's the angle theta. So let's write the given. And again, we are interested in how far its tip move, that means S. That's what we're interested in. What is a radius? 40 inches. What is theta? 20 degrees. And we want S equals R theta. So first and foremost, we have to change this to radians. So either d over 180 equals r over pi, or just multiplied by pi over 180. Either way, you end up with pi over 9 radians. So the conversion shouldn't be a big deal. S equals r 40 times theta pi over 9. 40 pi over 9 is precise, roughly 13.962. They want 2 decimals. The reason I'm showing you this, they want 2 decimals. When I look at this one next to it is 2, so it remains unchanged, 13.96 units of the radius, inches. Example 11, a water sprinkler is to cover a field of 100 square yards in the shape of a sector of a circle of radius 15 yards. What is the angle needed for this rotation? Again, we're going to go with 2 decimals. Let's write. The area of a sector has the formula half of r squared, and what is given is 100 yards squared as the area. The radius is 15 yards, and theta, this angle, is missing. So plug in. A equals 1/2 r squared theta. And so A will be replaced by 100. R will be replaced by 15. Fifteen squared is 225. So 2 times 100 divided by 225, or 100 over 112.5, or 8 over 9 radians. So it's 8 over 9 radians. Because this class is 225 divided by 2, which is 112. So 8 over 9 radians. For a case like that, they want it in degrees. So you can replace the radians, find the D. Again, I just wanted to show you that methodology. So close to 51 degrees, 50.93 degrees, because you have to make the conversion. A windshield wiper's arm and its blade are 30-inch long. So this is the situation. The entire thing is 30. This is the arm, this is the blade. If the blade is 24 inches long and the wiper sweeps about the angle of 125 degrees, the angle 125 degrees, how much window can it clean? How much window area? That means we want the area following the area of a sector, half of r squared theta. But let's understand what is given. First and foremost, this is the entire arm and blade of 30 inches. This portion, or this portion, if you will, it might be easier to see it here, is 6 inches. This is the arm. And therefore, arm and blade, we call them R1, arm. This much is arm, this much is blade, blade. So they add up to 30 inches. We call them R1. So arm and blade, or R1 is 30 inches. Arm is R2 or R1 minus 24, and theta is 125 degrees. And we want this blue shaded region or area. And of course, this arm is 6 inches or 30 minus 20. So we can use the 30 and calculate the entire area of the shaded region and area A and area B. So calculate the area of the window and this arm that covers, and then calculate this gray region, subtract from it. So half of R1 squared theta minus half of R squared theta. R1 squared is the longer R, and R2 is the smaller. So we have everything. R1 is 30 inches, R2 is 30 minus 24 or 6 inches. It's given here. And theta is 125 degrees. We multiply it by pi over 180. We get 25 pi over 36. I'm assuming this conversion is easy for everybody. Okay. You can go with d over 180 is r over pi, or just multiply by pi over 180. Either way, 25 pi over 36. And we're going to keep it as exact for now. Whenever you do calculations, you keep the intermediate steps exact, everybody. So plug in. Just plug in. So half of 30 squared times 25 pi over 36 minus half of 6 squared times 25 pi over 36. So this one 30 squared times 25 divided by 2 times 36, and we get 11 250 pi over 36. And this one half of 6 squared times 25 divided by 36, we get 450 pi over 36. I kept it as pi over 36 because I wanted to have the same denominator, so we can combine these two into 300 pi precisely. And now you use a calculator. They want 2 decimals, 942.48 inch squared. Units of the radius squared. That would be the units of area. An object is traveling around a circle of radius 2 meters. It travels 5 meters in 20 seconds. What are the angular and linear speed? So let's write the given. The radius is 2 meters. It travels 5 meters along a circular path. That means it covers S equals 5 meters over the course of time, 20 seconds. And therefore, we want V and omega. By definition, V is S over T. Five over 20 makes it 1/4 units of the numerator over the units of times, meters per second, meters per second. So that would be linear speed or velocity. We also know V equals R omega. Therefore, omega is V over R. We found V to be 1/4, R is 2 meters, so divided by 2, make it 1/8 radians per second. Radians per second. Pretty straightforward. A centrifugal force ride similar to gravitron and amusement ride spins at 22 revolutions per minute. If the diameter of the ride is 12 meters, what is the linear speed of the passengers in kilometers per hour? And these are some pictures to give you the idea. Let's write the given. 22 revolutions per minute, that's omega. Omega is 22 RPM. Radius, 12 divided by 2, because the diameter is given. Linear speed, V is a question mark. So omega is 22 RPM, revolutions per minute. R is 12 divided by 2 because it's not the radius, it's the diameter, 6 meters. You know D is 2 times R. And we are looking to find the velocity, the linear velocity V. First and foremost, we know omega is 2 pi times RPM because a complete revolution is 2 pi radians, and we want to change this from revolution to radians. So times, in order to go from revolution to radians, we're going to multiply by 2 pi. And we keep it exact, 22 times 2, 44 pi radians per minute. Intermediate steps, keep them as exact. Eventually, you could change that to an approximation, but not the intermediate steps. V equals R omega. And we know R to be 6, omega is 44. We end up with 6 times 44, 264 pi meters per minute. Meters per minute. Remember, this was in meters. And all is fine so far. So we are going to write 264 pi meters per minute, but we want to change it to kilometers per hour. By the way, just remember 1 mile is about 1.61 kilometers roughly. Okay, so 1 kilometer is 1,000 meters. And again, the unit conversion, I'm going to write it here. You could write 1,000 meters over 1 kilometers or 1 kilometer is about over 1,000 meters. The unit conversion, both of them are correct. Which one do you need? That's the key. We want the kilometer to remain at top. That's why you put it at top. 1 hour is 60 minutes. So 60 minutes over 1 hour or 1 hour, 60 minutes. Which one? 1 hour over 60 minutes. You want the hour at the bottom. So now notice what happens. This cancels at this one. This cancels at this one. And I just want you to look at the units. Left kilometers over hour. Now, that means 264 pi times 1 doesn't change, times 60 divided by 1,000. And we are going to use an approximation now for pi using a calculator. Results in 49.763 kilometers per hour as far as the number of decimals, whatever that they tell you. A DVD drive has a maximum speed of 7,200 RPM, revolutions per minute. If a DVD has a diameter of 12 centimeters, what is the linear speed in kilometers per hour of a 0.5 centimeters from the disk's center if it's spinning at a rate of 5,400 RPM? First and foremost, I want you to know the following. So if you have this, and this maximum is 7,200, what matters is where it's sitting. It's sitting this is 7,200, I'm sorry, RPM. This is 12 divided by 2. It has a diameter of 200. Okay. But what matters is that where is this sitting? This is sitting not at 6, but sitting at 5. So the radius that we are going to use is 5. This is the maximum speed, but it's not going at that speed. It is going at a different speed. So that's the key first I want to make. Let me erase mine. So this is the maximum speed. We don't have anything to do with that. This is the diameter, the radius is 6. We don't have anything to do with that. The reason why, where is this sitting? This is sitting at R equals 5. It's spinning at what rate? 5,400 RPM. So that's important to know. So that's a piece of information. That's a piece of information doesn't come to our calculation. V equals R omega. So before we get to V, we have to find omega in radians. So 2 pi times 5,400 because it's 2 pi times RPM. 2 pi times 5,400 is 10,800 pi radians per minute. So we are going from RPM, revolutions per minute, to radians per minute. Now V equals R omega. V equals R. Why are we using 5 and not 12 over 2? Because that's where it's sitting at. 5 times this one. And that gives us 54,000 pi centimeters per minute. Why centimeters? Units of the radius per units of time, minutes. So again, when we look at this, this is done, except if we want to change it to kilometers per hour, we are going to write 54,000 pi centimeters per minute is going to be how many kilometers per hour. So again, we are going to have a unit conversion. Remember, centimeters. 1 kilometer is 1,000 meter. 1 meter is 100 centimeters. 1 hour is 60 minutes. We're going to have all of those. Again, class, remember, you want kilometers at top, you want hours at the bottom, okay? So 1 kilometer over 1,000 meter, 1 meter over 100 centimeter, and 60 minutes over 1 hour. And again, take a look at what happens here. So centimeters cancels out the centimeters. Minute cancels out the minute. One from the top, one from the bottom. What is a different color now? And meter cancels out the meter. So if you look at what is left, in the numerator, there is no other unit except kilometers. In the denominator, no other units except the hours. So 54,000 pi times 1 times 1 times 60 divided by 100,000. 100 times 1,000. And that gives us 101.8 kilometers per hour. Example 16, the radius of each wheel of a car is 15 inches. If the wheels are turning at a rate of 3 RPS, revolutions per second, now this S is seconds, how fast is the car moving? Express your answer in inches per second and in miles per hour. Let's write the given. R is 15. Omega is 3 RPS. And we are looking for V. That's the translation. If you do that, it makes life easier. So what is given? Omega is 2 pi times 3 because this is RPS and it makes it 2 pi times 3 or 6 pi radians per second, everybody, per second. V equals R omega. V equals R omega. 15 times 6 pi is 90 pi inches per second, roughly this much. We're going to keep this exact for the next step. 90 pi inches per second, roughly 282.7 inches per second. We are going to go from inches per second to miles per hour, reminding everyone 1 mile is 5,280 feet. So obviously 1 mile is at top because we want the mile at top. 5,280 feet is at the bottom. 1 foot is 12 inches. 1 hour is 3,600 seconds because it's 60 times 60. Look at the methodology. You have to put the foot at top to cancel this one. You have to put the inch at the bottom to cancel this one, and so forth. So again, do we put 1 over 12 or 12 over 1? Think about the end result that you want. The same thing here, the same thing here. And so I'm going to cancel out what I can. So this one cancels out this one. Seconds cancels out the seconds here. Let's see what's left. I'm just looking at the units. The units, the only units left in the numerator is miles. The only units in the denominator is hours. So all you have to do, multiply 90 pi by 1 by 1 by 3600 divided by 12 times 5280, and we get 16.1 miles per hour. The mean distance of Earth from the sun is 9.29 times 10 to the power of 7 miles, assuming that the orbit of Earth around the sun is circular, and it's not, but it's close. So this is not the same as this one, and that one revolution takes 365 days. Again, it's not true. It's 365 days and 1/4 of a day. Find the linear speed of Earth in miles per hour. So there are some approximations here. So first and foremost, we have to look at what is given everybody. Remember, we are ultimately looking for the V, and the radius is this much. One revolution, a complete revolution around the sun, per year. That means one revolution per 365 days. So first, this is the R. Secondly, omega is one revolution per 365 days. So I'm going to read this as RPY, revolutions per day. We are going to change it to RPD, revolutions per day. This is revolutions per year, Y. RPD, revolutions per day. RPH, revolutions per hour. So omega is theta over t. A complete theta is one revolution, or 2 pi radians. So one revolution is 2 pi radians divided by 365 days. We want to make it revolutions per hour. 1 day is 24 hours. So we are going to multiply by 1 over 24, 1 day per 24. And again, notice that these two cancel each other. Again, I want you to see how these things work. So 2 pi two cancels out, the 24 becomes 12. So precisely pi over 12 times 365 radians per hour. I'm going to keep this exact for now. So V is R omega, everybody. V is R omega. R omega. R is 9.29 times 10 to the power of 7. And omega, we're going to keep it exact, as I mentioned. And the result will be miles per hour. You are going to multiply this one by pi, divide by 12 by times 365, and we end up with 66,633.324 miles per hour. So at a speed of 66,633.324 miles per hour. That's how Earth is moving around the sun. That's the speed. Almost 67,000 miles per hour. Unbelievable. 67,000 miles per hour, roughly. Okay, two pulleys, one with radius 2 inches and the other with radius 8 inches. So this is 2, this is 8. The bigger one, 8 inches. The smaller one, 2 inches of radius. Are connected by a belt if the 2-inch pulley is caused to rotate at 3 revolutions per minute. So it's going to do 3 revolutions each minute. Determine the revolutions per minute of the 8-inch pulley, and what about radians per minute? And the hint is that when that happens, class, their linear speeds, the linear speeds of the pulleys are the same, both equal the speed of the belt. That is fascinating. So as the belt is moving, the same speed it gives to each pulley. So this one, let's say R1 is this one 2 inches, this one 8 inches, and omega 1 is 3 revolutions per minute for the smaller pulley. We are interested in omega 2 for the bigger one. So they have equal velocities, and therefore for this one, we're going to write R1 omega 1, right? Here's the formula, R1 omega 1. For this one, we're going to write R2 omega 2. And we're going to replace what we have. For the smaller one, R1 is given to be 2, and omega 1 is given to be 3. For the bigger one, R2 is given to be 8, omega 2 is missing. So simply put, 6 divided by 8, 3/4 of a revolution per minute. And we are done, except if you wanted radian in per minute, then RPM. So you have to multiply the 3/4 by 2 pi, and that becomes 1.5 pi radians per minute. It just depends on the units that you're interested in. Earth rotates on an axis through its pole. The distance from the axis to a location on Earth 40 degrees north latitude is about 3,033.5 miles. Therefore, a location on Earth at 40 degrees north latitude is spinning on a circle of radius 3,033.5. Compute the linear speed on the surface of Earth at 40 degrees north latitude. So what is given? The radius is given. and omega is 1 revolution per day. We want the velocity, the linear speed. So it spins around itself. We want to find that speed. So omega is 1 RPD, short for revolution per day, which means times 2 pi makes it radians per day. So it does 2 pi radians per day. If I divide this by 24, I get pi over 12 radians per hour. Let me just make sure everybody is following what we are doing here. We have 1 revolution per day. A revolution is 2 pi radians, so we do 2 pi radians per day. A complete revolution per day is 2 pi radians per day. There are 24 hours, so if you divide this one by 24 hours in a day, 1 day is 24 hours, that would be pi over 12 radians per hour. So in 1 day, it goes around itself completely, 1 revolution. In 1 hour is 1 over 24 times that. So 2 pi radian divided by 24 is pi over 12. V equals R omega. We have R. Now we found omega. Now you put it into a calculator. Roughly you get 794 miles per hour. So about 800 miles per hour. The Earth is revolving about itself at that speed, 800 miles per hour, while going around the sun about almost 67,000 miles per hour. Fascinating. To approximate the speed of the current of a river, a circular paddle wheel with radius 4 feet is lowered into the water. If the current causes the wheel to rotate at a speed of 10 revolutions per minute, 10 revolutions per minute, what is the speed of the current in miles per hour? Well, let's write what's given. R is 4. Omega is 10 revolutions per minute. V is missing. Revolution per minute, we go with 2 pi times RPM. So 2 pi times 10 makes it 20 pi radians per minute. V equals R omega. We plug in. R is 4. Omega is 20 pi radians per minute, because 4 is 4 feet. the units become feet per minute. Okay, everybody? So because this is in feet, this is in radian per minute, it's 4 times 20 pi, or simply 80 pi feet per minute. We want them in miles per hour. 1 mile is 5,280 feet. 1 hour is 60 minutes. So we want miles per hour. 80 pi feet per minute. Let's write it in this manner. 1 mile over 5,280 feet, 60 minutes over hour. And notice again, I want you to see the units. Okay, feet cancels out. Minutes cancels out. And so if you look at the units in the numerator, nothing but miles, units in the denominator, nothing but hours. So now you're going to multiply 80 times pi 160 and divide by 5,280 gives you 2.86 miles per hour. So this would be an interesting methodology to find the speed of a current in a river. A Ferris wheel whose radius is 30 feet takes 70 seconds for 1 revolution. What is the linear speed in feet per second of this Ferris wheel? What is the angular speed in radians per second? So what is given? When we read the question, we notice the radius r is 30 feet. And it takes 70 seconds for 1 revolution. That means omega is 1 revolution per 70 seconds. So r is 30. Oh, so omega is 1 revolution per 70 seconds. V is missing. So omega is 1 revolution. That means 2 pi radians divided by 70 seconds, or pi over 35 seconds. Again, this is precise, everybody. Pi over 35 radians per second. V equals R omega. R omega. 30 times omega pi over 35, which makes it 6 pi over 7 feet per second, the units class. It's better to write this as radians per second here, so it becomes clear. And this one as feet per second. Again, this is exact. You can approximate it by changing the pi, everybody.